Hello everyone, this is Professor Srivinay, Computer Science Engineering Department, School of Engineering, Presidency University, Bengaluru. Today's session we will be learning about fast addition. To understand the concept of fast addition, first we have to see how a normal addition is performed by a computer. So now let us see the working of normal addition. A basic operation in all digital computers is the addition or subtraction of two numbers. In this topic, we discuss about the logic circuits used to implement addition operation. The time needed to perform an addition operation affects the processor's performance. Definitely. So here we have to learn how a normal addition works, find out the drawback of a normal addition, and learn how fast addition helps in overcoming the drawback. In this topic, we discuss about some of the techniques used in modern computers to perform arithmetic operation at high speed. The arithmetic operation considered here is addition operation. Addition and subtraction of two numbers. Consider the addition of two numbers x and y with n bits each. Because computer performs operation on binary numbers, so we are considering n bits. Say it might be an addition of 4 bits, 8 bits, or 10 bits, or whatever it is. Figure below in the next slide shows the logic specification for a stage of binary addition. You're going to see that shortly. The figure also shows the logic expression for these functions along with an example of addition of 4-bit unsigned numbers 7 and 6. The logic expression for sum, SI, and carryout function CI plus 1 are also shown in the figure. Now let us see that figure. So if you can see here, we have to perform x plus y equal to z. So we have taken in two unsigned numbers 7 plus 6 which is equal to 13. 7 in binary is 0, 1, 1, 1 and 6 in binary is 0, 1, 1, 0. Now when you start doing the addition of each stage, how many stages are here? This is the 0th stage, this is the first stage, this is the second stage, and this is the third stage. Totally from 0 to 3, 4 stages are there. We have considered a 4-bit addition. In the 0th stage, we have the x input as 1, y input as 0, and initial carry, we have assumed it as 0. So 1 plus 0 plus 0, sum is 1, and carry to the next stage is 0. And in the first stage again, x input is 1, y input is 1, carry input is 0. So 1 plus 1, 0, 0 plus 0 is 0, and carry is 1 to the next stage. Again, in this stage, you can see the inputs x and y are both 1. The carry input is also 1. So 1 plus 1 plus 1, sum is 1, carry is 1. And in the last stage, x input is 0, y input is 0, but the carry in is 1. So the sum is 1 and carry out is 0. So here we are considering only one stage and we have to see all possible combinations that we get to design a circuit. So here we have taken legend for the stage I. So we have considered the first stage here. In every stage, we will be having input xi, input yi, carry in represented as ci, sum is represented as si, and carry to the next stage we are considering as ci plus 1. Ci is the carry in, carry out we are considering as ci plus 1, carry to the next stage. So if you observe here, in every stage, we are having three inputs, xi, yi, and carry in ci, and two outputs, si and ci plus 1. So if you consider three inputs here, we can get around 8 different combinations because with 3 input 2 power 3, 8 different combinations will be getting it. So we have to write the truth table. For all 8 combinations, we have to check what is the sum and what is the carry and design the circuit for the same. Now let us see that in the next slide. Here you can see we have xi, yi, carry in ci. 8 different combinations of inputs. And you can see here 0 plus 0 plus 0, sum is 0, carry is 0. 0, 0, 1, sum is 1, carry is 0. 0, 1, 0, sum is 1, carry is 0. 0, 1, 1, this particular combination, 1 plus 1, when it comes, sum will be 0, carry will be 1. Now 1, 0, 0, sum is 1, carry is 0. 1, 0, 1, again 2 ones are there, so sum is 0, carry is 1. 1, 1, 0, so sum is 0, carry is 1. And the last combination 1, 1, 1, which results in sum as 1 and carry also as 1. Now you can either consider a K-map for the simplification or any reduction mechanism. So if I consider writing an expression for SI, wherever there is a 1, the equivalent product term I'll be considering it. So 1 here, so the equivalent product term will be xi bar, yi bar, ci. So that is what I have written here. Plus again a 1 here, so xi bar, yi, ci bar. Then again a 1 here, xi, yi bar, ci bar. Then again a 1 here, xi, yi, ci. So this is the sum of product expression for SI. Even if you write a K-map for SI, all the ones will be independent. You will not be getting any particular combination for this particular output. So better you can directly write a sum of product expression. Though I cannot simplify this further, but I can make the equation look much simplified. What I've tried to do here is, how did I result in this particular expression is, there are 4 product terms, 1, 2, 3, 4. The first and the fourth term, Ci is common. When I take Ci as common, I result in a XNOR operation, Xi XOR Yi whole bar. And second and third product term, I can take Ci bar common, I result in Xi XOR Yi. So again, that looks like A B bar plus A bar B. I'm sorry, it result looks like A B bar plus A bar B. So A here will be Xi XOR Yi and B will be Ci. So again, I can write that as Xi XOR Yi XOR Ci. This you can just do it for your simplification. So final expression what I require for sum is Si equal to Xi XOR Yi XOR Ci. Now when I draw the K-map for Ci plus 1, I result in the expression Yi into Ci plus Xi into Ci plus Xi into Yi. This is the expression for carry out Ci plus 1. So you can clearly note here, I require a 3 input XOR gate to form the sum Si. And for carry, I require 3 2 input AND gate and 1 3 input OR gate to form my Ci plus 1. So let us see that here. As I said, I require 1 3 input XOR gate and 1 3 input OR gate and 3 2 input AND gate. So the circuit which is used to perform addition of 3 inputs and produce 2 outputs is called full adder. So you can look here, the circuit which is used to perform addition of 3 inputs, Xi, Yi and Ci, 3 inputs and produce 2 outputs. This circuit we call it as full adder. Now we have seen all combinations of inputs. What are the outputs that we get? We have designed the equation and we have drawn the logic circuit for the full adder. So inside the full adder, these circuits will be present. So this is just the logic for a single stage. Now, if you go back here, for every stage, I have 3 inputs and 2 outputs. I require one full adder. Again, for the next stage, I require one full adder. For the next stage I require one full adder, and for the final stage also I require full adder, because every full adder performs addition of 3 inputs and produces 2 outputs. And you can see here the same repetition. The circuit which performs addition of 3 bits is a full adder. It consists of 3 inputs and 2 outputs. Inputs are xi, yi, and ci, and outputs are si and ci plus 1. And block diagram of the full adder, you just saw it here. This is the block diagram of the full adder, where these two circuits will be present inside this box. And you have to note here, for a 4-bit addition, I require 4 full adders. And carry from the previous full adder will be propagated to the next full adder. Like that, each and every carry will either propagate or ripple through the cascade connection. So here you can see a cascaded connection of n full adder blocks can be used to add 2 n-bit numbers. Since the carries must propagate or ripple through this cascade, the configuration here we call it as n-bit ripple carry adder. You can see with the diagram here, I require one full adder for the 0th stage where my inputs are x0, y0, and initial carry c0, and some s0 and carry c1 to the next stage. In this stage, again I have an input x1, y1, some s1, and carry c2 to the next stage, and so on. This diagram, what you are seeing here, is a general n-bit ripple carry adder. And the reason for calling this as a ripple carry adder is my carries are rippling through the cascade. I hope this is clear. So the next concept, computing the add time. Basically, here we need to find out the time required to perform the addition. Time required to perform the addition depends on the delay of the logic gates. Because just now we saw that in a full adder, everything is made up of logic gates. Every gate will have its own delay. So let us see how to calculate the delay. Here I have taken NOT gate. If I give the input X, I get X bar. The meaning, if I give input as 1, I get the output as 0. But the output will not be generated instantaneously because the signal has to be passed from the input to the output. It has to propagate. So that delay, we call it as propagation delay, or also we call it as gate delay. More specific, as there is only one gate, we call it as one gate delay. Say suppose if I have one more NOT gate connected here, so we call the delay at the output as 2 gate delay. And one more thing you have to note, if I have one more additional gate which is present here, and to both the gates, if I apply the input simultaneously, both the gates will produce the output in the same time. So at that time, you can't say it has a 2 gate delay. When both the inputs to both the gates are given simultaneously, both of them will produce the output in the same delay. Say suppose I have one more NOT gate here, I give the input Y where I get Y bar. So what is the gate delay? It is one gate delay only because the inputs are applied simultaneously. So now let us see in our example, considering the 0th stage, what will be the gate delay? So in the 0th stage, you have seen the input is X0, Y0, carry in C0, sum is S0, and carry out is C1. You can see here, to generate the sum, if I apply the input Xi, Yi, and Ci simultaneously, my sum will be produced using only one gate delay. So look here, when I give X0 and Y0, which is available with me, along with C0, where the initial carry is 0, when I apply it, S0 will be produced after only one gate delay, as there is only one gate. But with respect to carry, when we give the inputs here as Y0, C0, which is readily available, X0, C0, again it is available, X0 and Y0. All the inputs are readily available with me. I'll apply the inputs simultaneously. All of them will produce the output in only one gate delay here. All the three AND gates will produce the output in one gate delay. And I require one more gate delay here for OR gate in order to produce C1. So C1 will be produced after two gate delay. Considering the zeroth stage, C1 is available after two gate delay and S0 is produced after one gate delay. So clearly note this. Here you get confused. For all three AND gates, I'm applying the inputs simultaneously. All three AND gates will produce the output in the same delay. So one gate delay here and one more gate delay at the output of the OR gate. Totally two gate delays I require for producing C1. Now, in our example, we have considered 4-bit addition. That means 4 stages of addition. 4 full adders will be connected in a cascade connection. Now we have to see the overall delay, what it is required to generate a 4-bit addition. Look here, cascade of 4 full adders or a 4-bit adder. You can see here 4 full adders are here and the inputs are x0, y0 to the 0th stage, x1, y1 to the first stage, x2, y2 to the second stage, and x3 and y3 to the third stage. All the inputs are readily available with me. I can apply the inputs simultaneously. But all the full adders can't perform simultaneously because each and every full adder here is dependent on the carry from the previous stage. So just now we learned that for the 0th stage, S0 will be produced after one gate delay and C1 will be produced after two gate delay. So in this full adder to generate S1, I require only one gate delay, but this full adder has to wait for two gate delay to get the C1. So two gate delay and its own one gate delay to produce the sum. So totally S1 will be generated after 3 gate delay and C2 requires 2 gate delays as usual, but it has to wait for 2 gate delay to produce C1. So C2 will be produced after 4 gate delay. Similarly, this full adder has to wait for 4 gate delay and uses its one more gate delay to produce some S2. So S2 will be produced after 5 gate delay and C3 will be produced after 6 gate delay. Similarly, for the last one, S3 will be produced after 7 gate delay and C4 will be produced after 8 gate delays. So you can clearly note the drawback of a normal adder here. As you keep on increasing the number of bit stage addition, the number of gate delays keep increasing. Nowadays, we are using a computer of 64-bit. If you start performing addition of 64-bit, the gate delay drastically increases. So for this reason, we have to see the working of a fast addition. That is the reason fast addition came into picture. Fast addition. It is also called as carry look ahead addition. Why? Because in the fast addition, you can clearly see here the drawback which we saw in the normal addition was carry. Carry was killing the time because each and every full adder can perform the addition, but it has to wait for the carry. So for this reason, we should see how these carries can be generated parallelly. Is it possible? Let us see what is the logic involved in it. So we shall just recall the equations. Si equal to xi xor yi xor ci, and ci plus 1 was xi into yi plus xi into ci plus yi into ci. This we just got it from the full adder circuit. Now there is no problem with si, so let us not touch this equation. Considering the carry equation, what are the changes made here? Ci plus 1 equal to xi into yi plus, what is common here, ci. So xi plus yi into ci. We can write this equation as ci plus 1 equal to gi plus pi into ci. There is a specific reason for calling gi and pi where Gi is xi into yi and pi is xi plus yi. Gi is called as a generate function and pi is called as a propagate function. Means here in addition, either my carry will be generated or my carry will be propagated. Generate as in, like say suppose your inputs are 1 and 1, definitely the carry will be generated. 1 plus 1 is 0, carry is 1. Or propagate as in whatever is the previous carry that will be propagated to the next stage. Let us look more closely into it. Now if you can see here, Gi and Pi are computed only from Xi and Yi and not Ci. A very important thing to note here. So you can see here Gi and Pi are generate and propagate function are dependent only on Xi and Yi and not Ci. Thus, they can be computed in only one gate delay after X and Y are applied to the inputs of a n-bit adder. The meaning of that is the Gi and Pi can be generated in only one gate delay because all the inputs are readily available with me. As soon as I give it to a adder, Gi and Pi can be generated using only one gate delay because I require one AND gate and one OR gate. For both of them, I give the inputs simultaneously. Both the function Gi and Pi will be formed in only one gate delay. Yeah. So the expression for Gi and Pi are called the generate and propagate function for stage I. Now we'll see we have four stages of addition: zeroth stage, first stage, second stage, third stage. So totally four stages are required. So each bit stage contains what? Each bit stage, four stages are here. Each bit stage requires an AND gate to form Gi, correct? OR gate to form Pi, and three input XOR gate to form Si, because Si is what? Xi, XOR Yi, XOR Ci. And there exists a problem called as fan-in our logic design. When the number of inputs to the gate increases, it will not perform efficiently. So a smaller change was made to avoid three input XOR gate. So they have worked on a simpler circuit. Let us just see that a simpler circuit can be designed to generate Gi, Si and Pi. Pi equal to Xi XOR Yi, which differs from Pi equal to Xi plus Yi only when Xi equal to Yi equal to 1. What is the meaning of this? When you write a truth table for a OR gate, which is Xi plus Yi, and a truth table for XOR gate, only for the combination Xi and Yi, when both are 1, these two will change. Just look at it. When you give Xi and Yi as 0, 0, OR gate output will be 0, XOR gate output will be 0. When will the XOR gate output be 0? When both the inputs are same, output is 0. So when you give Xi and Yi 0, 1, OR gate will be 1, XOR gate will be 1. When you give input Xi and Yi as 1 and 0, OR gate produces the output 1, XOR gate also produces the output 1. But when you give 1 and 1, OR gate will produce the output 1, but XOR gate will produce the output 0. But here, if you note in our expression, when both are 1, Xi and Yi both are 1, so Gi itself will become 1. Definitely the carry will be generated even if it is not allowed to propagate. So 1 plus whatever, let it be Pi, I don't care. Either it is a OR gate or a XOR gate. Even if it produces 0 or 1, 1 plus whatever it will be 1. So definitely the carry will be generated. So here you'll get to know what was the reason for doing this, which eliminates the three input XOR gate, because as I've already used XOR gate to form Pi, so to form Si, only one more input Ci will be considered to generate Si, which is Xi XOR Yi XOR Ci. So more, we'll look at the diagram. I'll explain this again. So here you can see that But in this case, that is xi equal to yi equal to 1, gi is 1, so it does not matter whether pi is 0 or 1. Definitely the carry will be generated. Then using a cascade of 2 input XOR gate to realize the 3 input XOR function, the basic B cell can be used in each bit stage cell as shown in the figure. Now you can see this figure here. To form GI, I require one AND gate. No changes in this. Xi into Yi will form GI. Now to form Pi, instead of using OR gate, I'm using a XOR gate because we learned that only for one stage the output differs, but that doesn't matter as GI will produce the output as 1. So Pi is taken as Xi XOR Yi, and if you look here, the same output is given to the one more XOR gate, which is Xi XOR Yi, along with the input Ci. So together my Si will be Xi XOR Yi XORed with Ci. So you can clearly see in a B cell, there are only two input gates. We have avoided three input gates, which results in an fan-in problem. So this is the B cell. B cell as in bit stage cell. Here we have considered four stages. So I require four B cells. So now it is the time to look at the circuit of a 4-bit fast adder, where I'll be considering four B cells like this for the 0th stage, for the first stage, for the second stage, for the third stage. Let us look at the block diagram now. So you can see here B cell for the 0th stage, B cell for the first stage, B cell for the second, and B cell for the third stage. Now, as you see here, the inputs are X and Y. So for the 0th stage, it is X naught, Y naught. For first stage, it is X1 and Y1. For second stage, it is X2, Y2. And third stage, it is X3 and Y3. Where all the inputs are readily available with me, when I give it to the B cell, both G and P function can be produced in only one gate delay, as it is not dependent on the carry. So G naught, P naught, G1, P1, G2, P2, and G3 and P3 all will be produced in only one gate delay. Please make a note of this. All my generate and propagate function will be formed using only one gate delay. Now, all these functions, generate and propagate functions, are given to the box called as carry look ahead logic. So we have to look inside this box. What is the logic involved in order to generate these carries? Whether we have to check all these carries will be generated parallelly. That is the main aim of our lesson. So you can also see here the initial carry C naught, which is always 0, is also fed to this box. Now let us see the logic involved inside this box. We'll consider the carry equation, see whether all our carries will be generated in the same time. Unlike a normal adder, each of the carries was taking a additional time. If C1 was produced in 2 gate delay, C2 used to produce using 4, C3 used to produce using 6, C4 used to produce using 8. Now we have to see in this fast adder circuit whether all my carries will be generated parallelly by using the carry equation. So the logic involved in this is called carry look ahead. The name itself indicates you're going to look the carry ahead. So let us take the equation of the carry and work on it. Now, please recall our equation Ci plus 1 equal to Gi plus Pi into Ci. From the full adder carry circuit, I just got this equation. Now, I have to produce 4 carries, C1, C2, C3, C4, because C0 is initial carry will always be 0. So in order to get C1, I have to substitute I equal to 0 initially. When I substitute I equal to 0, it will become C1 equal to I is 0. So G0 plus P0 into C0. So to produce C1, let us draw the circuit for this. I require one 2-input AND gate to produce P0 and C0, and one 2-input OR gate to produce G0 plus P0 into C0. So if I've told you here in the beginning, G naught, P naught and all is already available in one gate delay. Keep this thing in your mind, one gate delay. One more gate delay for the AND gate and one more gate delay for the OR gate. Totally, to produce C1, I require 3 gate delay. I'll repeat this again. G naught and P naught function will be available after one gate delay. Here two gates are there. One more gate delay for the AND gate and one more gate delay for the OR gate. Totally, I require 3 gate delay. Good. Our concern is not C1. We have to see whether C2 also will be produced using the same time or it will increase. Now, in order to get C2, I have to substitute I as 1. So, C2 equal to G1 plus P1 into C1. Just look at this expression. Now, again, my C2 is dependent on C1. If I draw the circuit for this expression, again, there is no change. Again, C2 has to wait until C1 is produced. So somehow I have to make this expression independent of C1. So what is C1 from our previous expression? G0 plus P0 into C0. So G1 plus P1 into C1 is G0 plus P0 into C0. So C2 will now be G1 plus P1 G0 plus P1 P0 C0. Now, if you see our C2 expression, it is independent of C1. Let it be C0 because C0 will always be the initial carry, which is 0. Now, let us draw the circuit for this and check the delay required to produce C2. So, P1, P0, C0, 1, 3 input AND gate, and again P1, G0, 1, 2 input AND gate, and again we have G1 connected to the 3 input OR gate. Now, as I told you, all these functions G1, P1, G0, P0, P1, P0, if you had observed here, I told you all these generate and propagate function will be available after one gate delay because all the inputs here will be applied simultaneously. All my G and P function will be available after one gate delay. So if you look here, all my G and P functions here will be available after one gate delay. Again, both these AND gates will produce the output in one more additional gate delay. So 2 gate delay and one more gate delay I required to produce C2. So 1 gate delay for generate and propagate function, 1 gate delay for 2 AND gates, and 1 more gate delay for the OR gate. Totally, I require 3 gate delay to produce C2. So you can clearly observe here, both C1 and C2 are produced after 3 gate delay. You can look here in the circuit, all my G0, P0, G1, P1, G1, G2, P2 will be produced to this logic. Inside this box, these are the circuits which I have written here will be present in order to work on the carries. So if you can observe here, C1 is produced after 3 gate delay, C2 is also produced after 3 gate delay. Now we have to see whether C3 also will be produced after the same gate delay. For that reason, to produce C3, I have to substitute I equal to 2. So, sorry, I equal to 2. Yeah. So C3 will be equal to G2 plus P2 into C2. So I equal to 2 when you do it, C3 will be equal to G2 plus P2 into C2. Now, in this expression, my C3 is dependent on C2. In order to make it independent, you can look at the previous expression of C2, take this expression and substitute here so that you result in G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. So you can see here, I require one 4 input AND gate, one 3 input AND gate, and one 2 input AND gate, and finally one 4 input OR gate. If you can observe here again, all these G2, P2, G1, P2, P1, G0, all these functions will be available after one gate delay. One more additional gate delay for AND gates output. One more additional gate delay for OR gate output. So my C3 also will be produced after 3 gate delay. I hope you're following it now. So finally, in order to produce C4, we have to make I equal to 3. So C4 equal to G3 plus P3 into C3. In order to make independent of C3, I'm substituting the expression of C3 in this equation and finally getting this particular expression. Here also, after writing the logic circuit, you can note that all my G3, P3, G2, P1, G functions will be available after one gate delay, one more gate delay for the AND gate outputs, and one more gate delay for output of OR gate. Finally, C4 also will be produced after 3 gate delay. So a quick recap, I've drawn the same expression here. You can just see it, the expression for C1, C2, C3, and C4. In order to know more exactly what is that circuit that is available inside this carry look ahead logic, you can see here, this is the box, this is the circuit which I'm pointing. This is the circuit which will be available inside that carry look ahead logic. So you can look here, this is C0, sorry, C1, C2, C3, C4. But here we have produced this at a cost of what? The number of inputs to the gates keeps increasing. One of the drawback on this, but we have made sure all my C1, C2, C3, C4 will be available after only 3 gate delays. Unlike in normal addition, the gate delay was increasing. Here, if you keep on increasing whatever number of stages, it results in the same gate delay. So you can, a quick recap here to check all the functions. Pi and Gi are available after one gate delay. All carries are available after 3 gate delays, that is C1, C2, C3, C4. Now, if you observe in the circuit, G0, P0, G1, P1, G2, P2, G3, P3 will be available after one gate delay. Inside this box, there are circuits which is used to produce carries, which require 2 gate delay. So 2 plus 1, 3. So all my C1, C2, C3, C4 will be given back to the B cell in 3 gate delay. And when you give that carry to this XOR gate, it requires one more additional gate delay for XOR gate to produce my sum. S0, S1, S2, S3 will be available after 4 gate delay. A further one more gate delay which is required here because of this XOR gate. So just a quick recap. G0, P0, G1, P1, G2, P2, G3, P3 will be produced after one gate delay. When you give inside this box, all the carries require 2 gate delays. So 2 plus this generate propagate function, 3 gate delay. All these carries which produced in 3 gate delay will be given to the B cell. After the further gate delay, XOR gate delay, some will be produced after 4 gate delays. So that is what is written here. After a further XOR gate delay, all sum bits are available. So after 4 gate delays, all sums will be available. So the complete 4-bit adder was shown in the figure above. An adder implemented in this form is called carry look ahead adder, or also it is called fast adder. Delay through the adder is 3-gate delay for all carry bits and 4-gate delay for all sum bits. In comparison, 4-bit ripple carry adder, that is the normal adder, requires 7-gate delay for all sums and 8-gate delay for all carries. So here we have a reason to tell the circuit which we implemented is called a fast adder. If we cascade a number of 4-bit adders as shown in the figure above, possible to build long adders. Thank you.